Okay, it's recording has started. I'm going to share my screen. Okay. So let me play full screen. Okay. So today we are going to continue to talk about the nature of light and matter and their interactions. Last time we talked about the nature of light, and we said that light is not only a wave, but also a particle. It behaves both like a wave and like a particle. And today we're going to talk about matter and how they interact with each other. So first, I just want to start one poll to ask one review question for the relationship between wavelength frequency and energy. The longer the wavelength of a photon is, fill in the blank. Is it the higher its energy, the lower its energy, or the higher its frequency, or faster speed of light in vacuum? Please answer the poll quickly. Several haven't answered you. Some of you haven't answered yet. Some people just joined, so please answer the poll right now in the Zoom window. Okay, almost 100% of you got it correct. I'm going to end it and share it with you. So you all answered the correct answer. So the longer the wavelength of a photon is, the lower its energy. Because wavelength is inversely proportional with frequency. So longer is the wavelength, then the lower its frequency, and energy is proportional to frequency, so that if the frequency is lower, then energy is also lower. Okay, that's the only review question. Let me see. Stop sharing the poll results. Okay. So today we are going to first have a very brief review of the nature of matter, and then we are going to talk about how light and matter interact. So matter, in the universe, we not only have ordinary matters, but also dark matters. So here we're just talking about ordinary matters, matters that make up us, make up the earth, make up the stars, and almost all the stuff that we know of, we understand, all the stuff that we encounter in life, everything, they're all made of ordinary matters, and all ordinary matters are made of atoms. And what are atoms? Atoms are these very small particles inside matter. If you split a piece of cake into tiny bits, and then you continue to split it, and then eventually, when you break it apart into the smallest unit, those are the atoms. In an atom, you have not only a nucleus in the center that is made of protons and neutrons, you also have electrons going around it. And there, in the nucleus, depends on what kind of element it is, it may have more than one protons or more than one neutrons, sometimes no neutrons, sometimes several neutrons. So that the number of protons will determine what kind of element it is. And then you also have a number of electrons. If the atom is neutral, then the number of electrons will match the number of protons, because protons have positive charge and the electrons have negative charge. And so combined together, if the number of electrons is the same as the number of protons, then the atom is neutral. And because the proton has positive charge and electrons have negative charge, there is an electrical attraction force between them. And that is what holds atoms together. And that is atoms. And when you have more than one atoms together in a chemical bond, or you can form molecules. Molecules consist of two or more atoms, just such as water. Water is made of molecules, water molecules, and each water molecule has three atoms in it, two hydrogen atoms and one oxygen atom. And carbon dioxide also have multiple atoms in it, one carbon atom and two oxygen atoms. And ethanol or alcohol is made of two carbon, six hydrogen, and one oxygen. So in chemistry classes, you have learned many different kinds of molecules, but they're all made of atoms together, combined together. One thing that I want to say is that the scale in an atom is not the same as this picture that is shown in this figure. Just like at the beginning of this semester, I showed you the scale of the universe. Here also, we want to talk a little bit about a scale in an atom. The scale in an atom is that the nucleus is not as big as shown here. The nucleus is actually very, very tiny. The nucleus is about 10 to the minus 15 meters in size. So if you put what is this? This is I don't even know how to say this. It's like a zillion or meters or something. But if you, if you put 10 to the 15 nucleus, one next to each other, and that is 1 meter. And 10 to 15 is very large number, so the nucleus is very, very tiny in size. And the electron's orbit is about 10 to the minus 10 meters away from the center. And so we can see these two numbers that differ by 100,000, by 100,000, 10 to the 5th power, 10 to the 5th power. So the electron's distance away from the nucleus is much, much larger than the size of the nucleus itself. And so to put that in scale, that we really want to give some analogy to that so that you can imagine how big that is. So how big is that? If we imagine that we can make the atom much, much bigger, we scale up the size of an atom to the size of a football stadium, like the national stadium picture of China pictured in this image. If the nucleus is a grape, it's a little grape, we place that at the center of the field in this big, huge football stadium, and then the electrons would be like tiny flies, little flies that will be flying around the nucleus, but they're going to be far away from the nucleus. It will be flying in the cheapest seats you can find in the stadium, and so that very, very far away from the nucleus itself. The nucleus is like a grape, and then the electron is also very tiny itself, and it's like a tiny flies, and they'll be flying very far away from the nucleus itself. I see. Where are the cheap sheets outside? Yeah, they're now that them is cheap. Yeah, they're not that cheap, but the cheapest, relatively speaking, up here, there's the farthest seats away from the center. So what does that mean? That means most solid matter, most of the matters that we know about, is made up of mostly empty space, right? There's almost nothing. There's just a tiny grape in the middle of the field and tiny flies flying far away from it. So what are matter atoms really made of? Just mostly empty space. Is that really the case? Are we like this? Here's a person drinking water. Is that we are really empty? I mean, if you think about all the things that make up us, the nucleus and the electrons, they're just so tiny, and there's so much space in between them within an atom. So yeah, we are really made up of mostly empty space. Why don't we collapse, right? Why can't we still hold up ourselves? Why do we have solid matter? And how can they be so hard and solid, like this cup of mine? Why is it so hard? why can't we just break into the atoms and go through those empty space? So the reason is that although the space is very empty, if you try to go through it, or if you try to send some particles go through it, it will actually not be easy, because you'll always run into an electron, because the electron is not staying still, and the electron is not also orbiting the atoms like a planet orbit the sun. It's a very different picture. The electron is actually zooming around the nucleus in something called the electron cloud. And the electron is going so fast, and it's basically, you can say it is everywhere at the same time. And this is a very puzzling fact, is that the electrons is not located in any position for sure at any moment. If you say, okay, if you ask me, where is the electron right now in this atom? I cannot tell you. It could be here, it could be there. It's just that it actually a probability distribution of the electron's position. I cannot measure that precisely. I cannot tell you at any moment where an electron is in a nucleus and what its speed. Actually, its speed is not well defined. Electron is just everywhere in there. So you can say that in every second, the electron can go through every square meters of this stadium in 1 second. It can be anywhere. It can be everywhere. So you can say it is this part of the stadium, or you can say it at the same time it's at the other part of the stadium. The electron is basically going around the nucleus like crazy, you can say, and there is a probability that you can find it at anywhere. Just that there's higher probability finding it at some places than others. This is the realm of quantum mechanics. And so that is sort of what we know about these fundamental particles. They are not at any specific position in space at any given time. They have a probability of being anywhere. And they basically occupy a huge cloud. You can imagine that they're just zooming around really fast and going around the cloud, going around the nucleus. And it is this electron cloud that is hold up the solid matters. Because different atoms, they all have electron cloud around them. And these electron cloud cannot be pushed into each other. They will have electric repulsive force against each other. That when you try to push two atoms together, the electrons will push against each other because they want to occupy a certain amount of space. They don't want to be pressed into each other. So that is, these electron clouds are resisting against being pushed together. So it is that electrical repulsive force that is holding up materials. And so basically, you can say we're not really made up of empty space. We are made up of these electron cloud around nucleus. And that is what's going on that in most solid matters. And so electrons don't move on fixed paths about the nucleus like the planets about the sun. Instead, they can be thought of as inhabiting a probability clouds called orbitals. Yeah, we have some specific word, and we call that orbitals around the nucleus. It's not like orbits, but orbitals. And orbitals is referring to these specific regions, or some regions around the nucleus where it is most likely to find the electrons. And so we call those orbitals. And most of the space is basically occupied by these electron cloud, and the nucleus is very, very tiny in the center of each atom. And another fact is that these electrons, their orbitals, their probability distribution around nucleus is actually quantized. And that is how quantum mechanics got its name, because these electron orbitals are quantized. They exist only at particular energies, or you can say there's only particular configurations in this space within the atom where electrons can stay. So there are some specific configurations the electron cloud can take. They cannot take, I was just saying they can be anywhere, but it takes some different energy for them to go between these different orbitals. And these orbitals are just like an apartment building, and they have different floors. That you have a ground floor that is closest to the nucleus. And when the electron is at this orbital that is closest to the nucleus, it has the lowest energy. And if it is in orbital that is slightly further away from the nucleus, it is at a higher level in the atom. It's like a second level in the apartment building, and also there's third level and fourth level and so on. So to move an electron from one energy level to the next, you have to give it a specific amount of energy. And it cannot take any amount of energy. It has to be a specific amount of energy to move an electron from one level of orbitals to another level of orbitals. And so these are what we call the energy levels or electron orbitals in an atom. And that is, here is a schematic diagram showing what the hydrogen atom is like. In a hydrogen atom, we just have a single proton in the middle, and hydrogen atom only, because it has a single proton, it just have a single electron. So that is one positive charge and one negative charge. So they cancel out so that the whole thing is neutral. And in this simplest atom, the electrons can take several different orbitals. And in the ground state, we say that is the orbital that is closest to the nucleus. It has the lowest energies. And then we call that the ground state. And we use a number. We say the quantum number for the energy level. This is n equals 1 level. That is the ground state, the smallest level. And then there are other energy levels, and we just say, okay, this is the n equals 2 level, and this is the second closest, and then n equals 3, this is the third closest to the nucleus. And then the further away you are, the more excited the electron are, we say. And so those far away orbitals, they just have higher energies. And we call all these energies other than the ground level excited states. So the ground state is like the ground level of an apartment building, and then this is the second level, this is third level, and so on. And all these higher level, higher floors in an apartment building are these excited states for an electron. And outer orbitals have greater energy. So the higher it is, the higher is this n number, the higher is the energy of the electron. So that is sort of the basics. The electron have to have discrete energy levels. It's not continuous in an atom. So it can only take on these specific energies. It cannot stay in between two levels, just like you cannot stay in between two floors in an apartment building, right? You can only stay on specific floors. So this is how light will interact with these atoms. One electron in a hydrogen atom is at the ground state. If it ever wants to go to a higher level, you want to go from the ground state to an excited state. So that means it goes from the lowest orbital to one of the higher orbitals. It has to acquire additional energy because the ground level have the smallest energy, and the higher up levels, they have higher energy. So for the electrons to go higher, it has to have some energy to go there. Electrons are lazy. It's like that. I'm staying on the ground floor. Why do I want to go to upper levels? I don't want to climb the stairs. And you have to give me some energy so that I can climb the stairs to go to the upper level. And where does the energy come from? The energy can come from a photon. So if you have a photon coming in, and the photon is just of the right energy, the energy of a photon is Planck constant times its frequency. If the photon has just the right amount of energy, then electrons say, oh, great, I got this energy. And now I'm willing to do some exercise and climb the stairs and go to an upper level. And they say, okay, I have this much of energy that will allow me to go from level 1 to level 3. So it goes from ground state to excited state n equals 3. It doesn't have to go one level at a time. It can go jump between levels and can go from n equals 1 to n equals 3 directly if the photon have just the right amount of energy. And that photon's energy has to be equal to exactly the energy difference between these two levels, between the n equals 1 level and the n equals 3 level. So here I wrote the photon has to be equal to the difference in energy, and that equal to the third level energy minus the first level energy. So that has to be exactly the same. So there's a question, if the electron receives too little energy from a photon, why doesn't it just ignore the quantized energy levels? So if it has not the right amount of energy, it will get ignored by the electrons. The electron will not interact with that photon because it doesn't have the right energy for the electron to go somewhere. And you cannot really say, okay, I have this amount of energy, I split it into the amount of energy for me to go from n equals 1 to 3, and any additional energy, I just throw it away. You cannot throw it away into space in another photon. So that doesn't happen. So it only interact with a photon if it has exactly the same amount of energy between the n equals 1 and n equals 3 level. And when that happens, the photon disappears because the energy that's carried by the photon has been absorbed by the electron. And the electron goes from n equals 1 to n equals 3. This photon is like it's eaten by the electron. The photon just disappears. And we call that the absorption of a photon. So basically, the photon is absorbed by the electron, and it's really its energy getting absorbed, and the photon just disappears from the world in that case. But the energy is conserved. The total energy is the same because the amount carried by the energy get absorbed by the electron, so that the electron is now at an excited state at higher level. And as you were asking that if you have different photons coming in through the atom, only those photons that can match the energy difference between levels can be absorbed. All the other photons will just pass through as if the atom doesn't exist. So the photons can go through. All these other photons can go through. It's only that if this photon that have the right amount of energy that matches the energy difference between two levels, it can get absorbed. If it's too high or too low in energy, then it will just be ignored by the atom. On the other hand, if the photon has too much energy, if the photon has more energy than it is required to send the electron out of the hydrogen atom, then it can indeed kick the electron away from the nucleus, because there is only a certain amount of bonding energy to bond the electron with the proton, because their electrical force is bonding the electron to the proton, and that force is limited. That if you say that if you have, or the energy that the bonding energy is limited, that you have more energy if the photon carries too much energy, like it is an X-ray photon or it's a far ultraviolet photon, and that would be enough to kick the electron completely away from the atom. Just say send it all the way out of the hydrogen atom, and then in that case, the electron leaves the proton, and we say the atom is ionized. So that can also happen. So once the electron gets to one of these excited states, what will happen next? the electron actually does not like to stay at an excited state. It cannot stay there forever because these excited state, they're not as stable as the ground state. And so the electron that is on the excited state will want to come back to the ground state because they feel, okay, here it is too high. They don't want to be at an altitude. They really want to go lower. They want to go to the ground. And what, if it goes through ground, what will happen? It has to reduce its energy, right? And by how can it reduce its energy? It can reduce its energy by emitting a photon. So when the electron is jumping back from n equals 3 to n equals 1 level, a photon will be emitted. And the emitted photon will have exactly the energy difference between these two levels. And this photon will be basically the same energy as the energy that the photon that we just absorbed, right, in the previous slide. That it is going to be the same amount of energy because the difference between n equals 3 and n equals 1 is the same as the previously. So previously we absorbed a photon like this, and now we are emitting a photon like this. And when we emit this photon, the photon doesn't have to go through the same path as the previous photon. It can go into another random direction. This is now a new photon. Basically, we can say a photon is born or emitted, and it will correspond to exactly the energy difference between these two levels. And that also sets the frequency and the wavelength of this photon. It will be the same as before. So this is how atoms and photons interact. Atoms can absorb photons. It can also emit photons. But what energies those photons they emit or absorb depend on the configurations of these energy levels. And different atoms, like different elements, for example, hydrogen, mercury, carbon, nitrogen, oxygen, all these different elements, they all have different configurations for their energy levels. Here, this is the energy diagram of a hydrogen atom. We are plotting it like a ladder, and we are the height of these ladders, different levels of the ladder, represents how much energy there is between the levels. So for a hydrogen atom, you can see this is the ground state, and these are the excited state, and the n equals 2 level is very high up above the ground state. So it takes quite a big jump, quite a lot of energy for an electron to go from this level to a higher level. But then between these higher levels, the amount of energy required gets smaller and smaller as you go higher. So this is a hydrogen atom. Here is a mercury atom. And here we're talking about just the mercury has more than one electron. It has many electrons. But here we're just talking about the electron in the outermost levels, or the outermost electron. It has these specific energy levels. And for that electron to jump between energy levels, the ladders have different spacings as the hydrogen ladder. The mercury energy levels have a different spacing between them. And you can see it has many more levels at a lower energy. And so it wouldn't take a lot of energy to put an electron of a mercury atom from the ground state to an excited state, not as much as what you need to kick an hydrogen atom higher up. So every element will have a different configuration of the energy levels, and each element is unique in its configuration. And so that you can see they will interact with a unique set of specific wavelengths when they interact with light, right? They can absorb or emit those specific wavelengths. And so that is how the spectrum of these different atoms differ from each other. Each chemical element has a unique emission absorption spectrum because its unique configuration of energy levels. For example, this is the hydrogen's spectrum. These wavelengths, you see, this is a red light, this is a very long wavelength light, and this is blue and purple light. These are short wavelength light. And so what I'm plotting here is a spectrum of hydrogen. And these specific lines corresponding to different wavelengths of light. So by taking a spectrum of distant object, we can determine what it is made of, because these different atoms, they have different energy configurations in their atoms, and so they can interact with different light with different wavelengths. So I'm going to show you a demo before of how to make these spectra. But before I do that, I want to show you how spectra are made. Remember that white light can be decomposed into spectrum, right? White light can be decomposed into a rainbow spectrum from red, orange, yellow, green, blue, indigo, and violet, right? So then that is corresponding to different wavelengths, and you can do that if you put the white light through a prism, and this prism works as a dispersing element. It disperses the light into different wavelengths. So not only prism can do that, we can also use a grating to do that. So we say that prism disperses light. When we say disperses, we mean that it spread out light of different wavelengths, and so that it will make a spectrum. So if you have white light goes through a prism, you can make a spectrum. Another kind of device called the grating can also do this. A grating can be made by many different ways, but one kind of grating is transmissive, so that light goes through. But you can put some features in this film, in a transparent film. It's like a piece of glass, but then you carve some grooves in the glass. And when the grooves in the glass have a specific regular pattern, it will work as a grating, and it can also disperse the light. And it disperses light in two directions. And in each direction, it will spread the red light, green light, and blue light out from each other, and so that it can also make a spectrum. So what I'm going to show you in the next demo is that I'm going to show you the image you will look by looking through a grating. It's like we place our eyes here and looking towards where the light comes from. So if the white light comes from here, and then it gets diverted into that direction and also gets dispersed, we place our eyes here or place our cameras here. So in my experiment that I'm going to show you, I was going to put this cell phone at that location, at this location where my cursor is pointing at, and looking towards this direction, towards the grating. And then you will see what you can see through that. And here, remember, here are the emission spectrum of these different items. I'm going to show you the emission spectrum of some items. So I still have you online, everyone. And now let me actually show you a video. So if we were teaching in person, I would have this lamp in classroom, and I'll give some greetings to you guys to handle. But since we are now teaching online, I have to show you this video. I pre-recorded them in the lab, and just going to show you that. So let me know if you couldn't hear the sound from the video. So I'm going to play it now. You can see it almost full screen, right? Hello, in this demo, I'm going to show you how to see the spectrum lines from several gas lamps. So over here, we have a lamp that you can see a tube that is installed in it. And this tube contains a kind of gas in it. And in this case, it is helium. And I have a grating in my hand. This grating is a very thin film. And in the thin film, there's many tiny grooves that can diffract the light and disperse the light into multiple wavelengths. And so here we're going to put this grating in front of my camera so that you can see through the grating. And then we're going to use the camera
and looking through the grating at the lamp to see the spectrum lines. So now let's turn on the lamp, and you can see to the left side of the lamp, you have several additional lines. And so there's a purple line, a blue line, a cyan line, maybe two cyan lines, and then there's a yellow and a red line. And these are the images of the lamp. But they are images of the lamp in different colors. The lamp, the light coming from the lamp directly looks yellowish, but when it is dispersed, you can see it get dispersed into multiple colors, and there is strong emission at several particular wavelengths. So this is called an emission line spectrum, and you can see it is from this helium lamp. Now let's turn it off, and you can see the lamp will disappear. The spectrum will disappear, and if we turn it on, you can see it right here. And now let's turn it off and then change to a different lamp.
Okay, so you can see, you saw the video, right? Good. So you can see that, note that each of these lines have exactly the shape of the tube itself, right? You can see the top and the bottom of the tube and the middle part of the tube where it is brightest. All of these images are showing exactly the same thing, as you can see in this tube. So this is a tiny gas tube. We put some electric voltage going through it, and so in the tube there is this gas. And as I said, this is a helium gas tube, and now we can try to match this spectrum with the spectrum from helium on my slide and see if they actually match each other or not. So I'm going to make this small so that you can actually see these two at the same time. You can see my whole desktop, right? Yeah. You can just nod because I can actually see you. So that, where is helium? Okay, helium is on the third row. Can you see that whether this thing matches this? This is a helium spectrum as printed on my slides. I got this image from a textbook, actually. Do they match? You can type in the chat window if you have any reactions or have any questions. You can see that these lines are much closely spaced than these lines, right? Yeah, you can see they match, but some of you might be puzzled. Why are they so closely packed, but this lamp is so wide apart from each other? And that is because that you can imagine that this picture is actually just stretching this picture. So if I take an image and I stretch it in the horizontal direction, I can put them wide apart from each other. And also the resolution of the grating is different. So the resolution they use to take this spectrum is probably much higher than the resolution of the grating I was using. But you can see that the relative spacing between the lines are the same. For example, you can see that the spacing between this red and this yellow line is about the same as the spacing between the yellow and these two cyan lines, right? And maybe this side is a little bigger. And if you look at in this picture in the video, that the spacing between the red and the yellow line and between the yellow and the two cyan lines is about the same. And this side is also a little bigger. And you can see that this pair of cyan lines, indeed it is two lines. And I have two lines in my picture. And the spacing between these two lines is about 1/3 of the spacing between this one and the next one, right? This blue line in my picture. And here in my picture, this is also the spacing between the two cyan lines is also about 1/3 of that. So the spacing, relative spacing, is in proportion to each other. And so that this is exactly the helium spectrum. And you can see it matches quite well to each other. And you can also see there's some color mapping difference, that this line that we can see the bluest or the purple line, or the wave line with the shortest wavelength. It looks purple in my video, but it's plotted as blue on the slide. But that's just because the mapping of the colors is slightly different. And this may not be a real image. This may be just plotted in color by some computer program. And this is a real image of a helium lamp. Now let's look at another lamp and see if you can recognize what it is. I'm going to close this video and show you another one.
Now this is a different lamp. Let's turn it on. I'm going to put the grating again in front of my camera, so we look through the grating, and you can see a different pattern. Now you can look at this and compare it to the spectrum in the PowerPoint, and you can see which one it is.
Let's see which one is this lamp. I make it too small. I'm going to place it here. You can see there's some lines in this one, and there is the slide. Let me put it on the side. I want you to type into the chat window. You can type it directly to me to tell me what element you think this one is. Only got reactions from one person so far. Okay, a few of you have responded. Any more? There is some imperfections in the lamp, so there's some additional stuff, but you should just focus on the brightest features. Now I see many of you have recognized this is hydrogen. This is one on top here. You can see it has the brightest feature. There's a bright yellow, bright red line, and there's a cyan one, and there's a blue purplish one. And these corresponding to these three lines in the spectrum of hydrogen. You may wonder why there's a green line then. There isn't any green line. This I mean, if I zoom in this, there's some imperfections in there. That these stuff, I don't actually know what is causing that. That the hydrogen, I mean, first of all, the lamp itself is imperfect, that they may have some leakage of other elements in there, so there may have some other contaminations. It is maybe not only hydrogen gas is in there, some other gas that is mixed in, and also there are some scatters and reflections. Of course, you can see this picture is taken on top of a background. There's some other light source, maybe oh, I don't know. But anyway, I think these are coming from contaminant gas in the tube. But anyway, we can see these three major lines. Yeah, you must. That's right. So you must also always look at the most distinctive features. These ones. So those are the three lines here. And remember that this bluish line in this slide is actually kind of purple. Yeah, when it gets to about this wavelength, it will start to look like purple in real life. Okay, now next one.
Now we have changed the lamp the gas tube in the lamp to another different one, and guess what gas is in that. And again, this grating is for in front of the camera. I'll turn it on, and let's look at what it is. You see a purplish, bluish line, a green line, a yellow line, and some red lines, right?
Okay, let's see what that one is. Which one is this? This may get a little hard. We know it's not hydrogen. This looks different. It's not sodium. Sodium has just two yellow lines, and this one has green and blue. Which one is it? Yeah, many of you have said it's mercury. That's right. It is mercury. But does it look different from this mercury line? Mercury spectrum? This bottom one is mercury, right? Yeah, maybe there is indeed a double yellow line, right? There's a, so if you look in detail, this yellow line is a little different from the green one. The green one is narrow, and the yellow one, it looks like there is indeed two there, so that we have this yellow double lines, and then there's a green line. But where is the cyan line? Isn't the cyan line missing? And then there is indeed a purple one that, as I said before, that this blue color is kind of purple in real life. But we're missing the cyan line, right? This line is missing. It's not in there. And this is how real, when you do real experiment, it can look different from what you get in the textbook. This line is there, it just is much, much weaker than all these other lines. And may only become strong at certain temperatures of the gas. And so that is why this level is not actually excited in the mercury atom in this tube itself. That how do you produce these emission spectrum is that you have to pump the electrons to a higher level first. And then when they come back down to the ground level or lower levels, we can get these emission spectrum. So the conditions to form any of these spectrum lines is that you have to first be able to pump the electron to an upper level. If the electric voltage of this lamp is not high enough, or if the temperature of the gas is not high enough, we may not be able to pump the electron to the level that is actually required to generate these lines. So that is why it is really, really weak or non-existent in this lamp, in this particular experimental setup, so that you can have missing lines. But if you just compare the spacing between the yellow and the green, and between the green and the purple, you can see it matches the spacing between these two and these two. So you can see this one is about 5 or 6 times, the spacing between this green and the purple line is about 5 or 6 times wider than the spacing between the yellow and the green line. So that is about right. And so these, we have 3 lines matching, but we don't have the cyan line. So, but that is because the lamp is probably not hot enough to actually generate this line. That's great. That's mercury. And now I think I have one more, and that becomes obvious. First, let me answer a question. There's a question, are the emission spectra presented on the PPO the ideal temperatures of the gas, or are they all at the same temperature? Actually, I don't know. I don't know what conditions was used in generating this plot. I didn't generate the plot. So there's different conditions that certainly will play a role in making the slide. This one. Let's look at this one.
Now we have changed it into another gas tube. here in the lamp, and I'm going to look through the grating again, and you can see it is red and yellow color. And let's see that amazing group of lines. You see so many red and yellow lines and green lines. And guess what gas is in this tube?
So now that becomes obvious. I hope you can just now type in the answer in the chat window and tell me what that is. It's neon, right? Yeah, it's clearly neon. You can see that the neon has a lot of really bright red and orange and yellow lines, and this lamp has that exactly that. But in addition, it has some green lines, and it has some cyan and purple lines. Maybe these come from neon. It's just that this PowerPoint spectrum was not at that condition, so it didn't include those levels. Or there may be contaminants in the gas tube that is producing these extra lines. So you can see that in a real experiment, you can have either additional lines or you have missing lines. That can both happen. But how, and in astronomical objects is the same thing. When we take spectra of the gas in the interstellar medium, we sometimes get the same kind of phenomena as well. Sometimes we see more than what we expected. Sometimes we see less than what we expected. And that difference actually are the interesting things so that we can know what is going on. Why is the condition in the interstellar medium different from the conditions in the lab, and why are we having additional lines or having missing lines? And that is exactly how we tell what the stars are made of and how the galaxies, what elements the galaxies are made of. Okay, there's some additional stuff I'm going to talk about in the video, so I'm going to continue to play this.
Now, before we turn it off, let's also look at the other side. Let's use the grating to look at the other side. Note that in this side, the red line is on the left, the green line is on the right. So if we look at the other side of the lamp, you can also see a spectrum of this lamp. But here, the direction is reversed. The green line is closer, the green lines are now on the left side, and the reddish lines are on the right-hand side. See, this is a lamp. Here is one side of spectrum. And we look at this side, you see another side of spectrum. Okay, now let's turn this off.
So this is what I was saying earlier. So you can see actually two sets of spectrum. And that is because the grating has that feature that a grating will disperse light in two directions. It will actually bend it in two directions. And in my experimental setup, I'm actually putting the grating in front of the camera, but it's the same thing that in one set, you can see that the red light is on the right hand side, and in this way, the red light is on the left hand side, right? So that it just depends on which direction you're looking that you can get different spectrum. And notice that the blue light have the less bending than the red light. The red light bends more than the blue light. And it's the same thing in the video, is that you can see the blue light is closer to the lamp in both sets of spectrum. So that is matching what we are seeing here. Okay, and I'm going to continue to play the video. There's more.
You may have also wondered, what is this continuum spectrum in the middle? You see this beautiful rainbow that is made by red, orange, yellow, green, blue colors. They're beautiful. You wonder what spectrum is that? I tell you, that is the spectrum of the sun. And the reason is we have a door over there, and there's a window on the door. Some sunlight is leaking in through there, and that is producing a beautiful continuum spectrum of the sun.
So this is the spectrum of the sun. there is a, you can see there's a door over here, and there's a window, the slot on the door, and it actually we are looking through the, I mean, on the other hand of the hallway, there's another office with the door open and it has a window. Somehow the sunlight is leaking in through there, and that is making this continuous spectrum. You can see this spectrum is very different from the spectrum we are seeing in the lamps, from the lamps, right? There's no gaps in between the light. The light is continuous, so there almost at every wavelength you have something. And now you have basically red, orange, yellow, green, cyan, blue, indigo, and violet. So all the colors that we can recognize are in the spectrum. Okay.
Sun. And the reason is we have a door over there. And
okay, that's it for this video. So that is what we call a continuous spectrum. And it's different from the previous spectrum, which we showed is the emission line spectrum. So the one with many bright lines, those are emission line spectrum, and this is a continuous spectrum because there's no gaps in between in the middle. I also want to show another one. Oops. This shows you the spectrum of the ceiling light.
Now we have turned on the light. And now we can again use this grating to look at all the light sources, and you will find they can all be dispersed into different spectrum. So see, this is the ceiling light. And when I use the grating to look at the ceiling light, you can see it clearly also get dispersed into multiple lines. These lamps are fluorescent lamps, and they're not like incandescent light bulbs. They produce these discrete wavelengths. You can see red, green, cyan, and blue lines in these. And because we have multiple set of ceiling lamps, and you can see multiple set of lines. And they actually have the shape of the lamp itself. Each line is having the same shape as the lamp itself.
Okay, so that you can see there's about 5 lines in there. So these fluorescent lamps also have these are made by a certain kind of gas in the lamp, and they can generate certain emission spectrum. So these fluorescent lamps, they're when they look bright, it will look white. It's actually because they give out light at several different wavelengths, and combined together, this light looks white to us. Okay, that's it for this one, this video. Now we can go back to the lecture. And now, so that's what we did. So that now you understand that these the reason that we have different spectrum from different elements is because that the energy levels are different. The energy level configurations are different. Basically, the spacing between the energy levels are different, and that each element has a unique set of these spacings, and it will generate a unique set of emission line when it is making a spectrum. So that is how astronomers how astronomers can understand what elements astronomical objects are made of. We just take their spectra. We take spectra of stars and galaxies, and then we can just look at what features are there in their spectrum. But the spectrum we see are usually not as simple as the ones I'm showing you. I just showed you. It can have 3 kinds of spectra. There are 3 kinds of spectra we can see in astronomical objects: emission line spectrum, absorption line spectrum, and continuous spectrum. So I showed you an example of an emission line spectrum. I showed you an example of a continuous spectrum, which is the spectrum that is made by the sun. It is continuous. But we can also have a third kind called absorption line spectrum. because items can absorb photons, right? So here are what those spectrum look like. So here is an emission line spectrum. This one is one that is made by neon. And you can see in this one that I do have the green lines in there, not just the red and yellow. So you can see this one is actually a real one. This is taken using a real experiment. And this one is a continuous spectrum. This is actually a not real one, but yeah, you can see this looks like the same as the one I showed you, the solar spectrum I showed you that in the video. And what is an absorption line spectrum? To see an absorption line spectrum, you first have to have a background continuous spectrum. If you have a background continuous spectrum, sometimes in astronomical objects, we will see dark lines on top of it. At certain specific wavelengths, there will be a sharp drop in intensity. Basically, the intensity at these specific wavelengths is much lower than the surrounding areas. And these are what we call absorption line spectrum. These absorption line spectrum are also correspond to, the positions of these absorption lines are also corresponding to the energy spacings in atoms. So that the reason that they get absorbed is because that you have some atoms in front of a continuous spectrum emitting source, and then the atoms have some electrons at lower levels in their in those atoms, and when these photons pass through, certain specific wavelengths can get absorbed by those electrons, and so that those photons will disappear out of the view, and that is how we can generate absorption line spectrum. And so I'm just going to explain a bit more detail. How are they different, and how do we present this information more accurately or quantitatively? So now I think maybe it's good to take a very short break, and so that you can go to bathroom or whatever, and then we'll continue in 5 minutes. How about that? We'll take a short break now and then come back in 3:40. Thank you. Okay, let's come back and restart. Are you there? Oh, guys, back? Okay, good. Let me start sharing again. So as we sorry, play full screen. So as I was just saying that we have 3 different kinds of spectrum: emission line spectrum, a continuous spectrum, and absorption line spectrum, basically meaning having dark lines on top of a continuous spectrum. How are they different, and how do we present this information more accurately? A spectrum basically just shows you how the intensity of radiation varies with wavelengths. So you have astronomical objects and you take a spectrum of it. It may look like this. It may have bright lines on top of a continuous spectrum. And usually when we actually take the spectrum, we don't use color films, color photographic films. So we don't usually get colors directly, and these colors are just you can put on the colors afterwards. But what we get is that we just get photons with different energies, and whatever detectors that we use will record those intensity of radiation. And then later on in a computer, you can attach the colors to it. But if you use your eyes to look at it directly, you will see these colors, because that is the colors is to our eyes, the color reflects the wavelength difference. The color is basically our perspective, is our perspective of how the light looks, how the light of different wavelengths looks to us. So color here is just a rough guide to the wavelengths, and the brightness really represents intensity of radiation at a given wavelength. The wavelengths are changing and the intensity is changing as well. And so a more accurate way to represent that information is to use a graph in which we show intensity as a function of wavelength. So here is the wavelength of the light. And so this is wavelength in a spectrum going from ultraviolet to red, and even beyond red going to infrared. And our eyes actually cannot see this part of the spectrum, because our eyes are only sensitive from violet to red. So our eyes is only sensitive to this range of spectrum. But actually there is radiation beyond the violet, that's called ultraviolet, and radiation beyond red, that's called infrared, as I talked about last time, right? And you plot intensity as a function of wavelength, you can have a curve, and this curve is called a spectrum. What is a continuous spectrum? A continuous spectrum is one that you have some value at all wavelengths. And so you can say this is a continuous spectrum. And on top of the continuous spectrum, you may have some narrow features, and those narrow features are what we call emission lines. So that by narrow, I mean that they only occupy a single wavelength here, or a very small range of wavelengths here and there. And you can also have absorption lines, which means that it looks like the continuous spectrum have a shortage of energy, a shortage of intensity at certain wavelengths. And so these are called absorption lines. And in the spectrum, they will appear as dark lines, and here as well. So this is sort of a more accurate way of describing what is a continuous spectrum, and what is the emission spectrum, and what is absorption spectrum. A real spectrum can have all three kinds in it altogether. You can see like that. And so that here is a representation of a neon lamp spectrum. And you can see that if I make a spectrum, I make a plot, I'll plot the intensity versus wavelengths, and they don't have just very narrow lines and very strong and narrow lines at these specific wavelengths. But in between the lines, there's almost no flux, almost no light at all. And so that the levels go to almost zero in between. And here is a representation of a continuous spectrum, and our sun's spectrum looks very similar to this, and it's just a continuous distribution of light at all wavelengths. And then here is absorption. That's that. So now I'm going to talk about the physical mechanism of how to produce these things. To understand that, we need to consider what happens when we put a bunch of atoms together in the same place. So you have a box of gas. In the gas, you have atoms, and atoms are just moving around, right? They're moving around. They have random motions, and they collide with each other. And when they collide, their electrons can exchange energy and emit and absorb photons. So the simplest thing to understand is the emission line spectrum. That when you have something like the gas tube we had in our lamp, we get these kind of spectrum. So physically, what is happening? And this kind of gas is usually produced by a diffuse low density gas. So that is the same as what we have in the gas tube. In that kind of conditions, we have in the gas tube in the lamp, we are applying a electrical voltage on top of it. And so the electrons are actually zooming through the gas tube. We're sending electrons from one end of the tube to the other end of the tube with very high velocities. And those electrons is going to bump into this gas particles, gas atoms, and they will kick the electrons in the gas atoms from a lower level to a higher level. And when they get kicked to a higher level, they don't want to stay at those excited state forever, so they want to come back down. And when they come back down to ground level, they'll produce these emission line spectrum. And in all kinds of low density diffuse gas, you get the same thing. It's just collisions, random collisions between atoms, and collisions between electrons and atoms can basically bump the energy levels to higher up. And then when the electrons can bump to higher levels, they will always come back down and produce emission line spectrum. So low density gas always produce emission line spectrum. How can you produce this continuous spectrum? To produce this, you need a very dense gas, like the interior of the sun. The sun is still a gas, but it is much denser and it's at much higher temperatures than our atmosphere. And also that things like a solid matter can also produce continuous spectrum. For example, this is an incandescent light bulb. This is the old kind of light bulb. So nowadays, it's actually very difficult to find them because they are not very energy efficient. But in the old days, we have these kind of light bulbs, and in the middle, you have a wire filament, usually made of tungsten, and it's a kind of metal. And this wire filament is a solid material. And when we put electric charge on it, and it will go to a very high temperature, several thousand degrees. And when they're at several thousand degrees, it can produce this continuous spectrum. How can they produce that? And the reason is that in a solid material, that the individual atoms are packed very closely to each other, and their energy levels get perturbed. They're no longer at the original energy levels as they were when they were isolated, like in a gas. And the collisions also becoming very frequent in the solid material or in the dense gas, dense opaque gas. And the strength of collisions determines what energy of the photons can be emitted and can be absorbed. For example, in the sun, that the gas are very densely packed. You have lots of atoms and lots of protons and electrons very close to each other. And so whenever they collide, they can exchange energies and they can also produce photons. And it is those collisions that are producing a range of photons with a range of energies or with a range of wavelengths. Some collisions are strong and they will produce very high energy radiation. Some collisions are very weak. They will produce very low energy radiation. But most of the collisions are going to be somewhere in between, right? They'll produce something that of intermediate energy. Because high energy collisions are rare and low energy collisions are also rare. It's just the middle energy range is most common, so that you will have most of the collisions happen at this intermediate regime. And the resulting spectrum will be a continuous spectrum that will have a range of wavelengths. They can basically have all kinds of collisions that will produce all kinds of photons with all kinds of energies, all kinds of wavelengths. But the one that is most common will be in the middle, and so that you will have a peak in the middle. And this is what we call the thermal radiation. The peak of this, where the intensity is strongest, this depends on what is the most common collisions between the atoms or between the protons and electrons. And the most common collision will depend on how hot the gas is or how hot the solid is. The solid material, the hotter the solid material, the faster the atoms will be moving inside, right? And when they're moving faster, they will have more energetic collisions. And more energetic collisions will give you light with higher energies and the peak will shift towards short wavelengths, because short wavelengths corresponding to higher energy photons, right? So that if you heat up the thing even more, the peak of the radiation will move towards shorter wavelengths. So that's why we call this thermal radiation, because the characteristic of this radiation is totally dependent on the thermal property or the temperature of the material that is radiating. So that is how you produce continuous spectrum. And then what about an absorption spectrum? To produce an absorption spectrum, first you have to have a continuous spectrum source. For example, a hot light source, incandescent light bulb, or you have a star. Here, it will produce a continuous spectrum. And if there's a cloud of gas that is staying in front of the star, and the light passes through the cloud of gas, and the gas is of a cooler temperature than the star itself, then the atoms in the gas cloud will be able to absorb some specific energies, because there are electrons in the cloud of gas. They're staying at the ground level waiting to be excited, right? And if you have a bunch of photons coming in with all kinds of energies, they will be able to pick out those specific photons that have the specific energies that they can take to go to higher levels. And so that the atoms in the gas cloud will be able to absorb these specific wavelengths and basically eat up those photons. And so that in the spectrum that passes through the cloud, you will have a shortage of energy, shortage of flux, or shortage of intensity at those specific wavelengths. So that on top of a continuous spectrum, you're going to start having some darker lines, darker compared to their nearby regions, but maybe not completely dark, because not all the photons at those energy can be completely absorbed. They get absorbed by maybe 50% or 40% or whatever. And then when you take a spectrum, you get this kind of thing. So if you have a cool cloud of gas in front of a hot light source, you can get an absorption spectrum. So that is how you produce absorption spectrum. So here, this slide summarizes the three kinds. That the top one is a solid material or star. Sorry, I want to get rid of the top bar, but anyway, this solid material or star, it will produce a continuous spectrum with light everywhere. And then if you just have a cloud of gas by itself, there's no background source, and then you will see emission line spectrum. And if you have a cool cloud of gas in front of a hot light source, you have a continuous spectrum, and on top of it, you have an absorption line. So this is called an absorption line spectrum. Any questions so far? Okay. And so I want to talk more about the thermal radiation. The thermal radiation is actually the most common radiation we have in universe, because all the stars are making these kind of thermal radiation. Actually, all objects are making these thermal radiation. Any object that have a temperature will make this a thermal radiation spectrum, including ourselves. We have a temperature, right? We have a body temperature about 36.5 centigrade, and that we are actually also making a thermal spectrum, and that is emitting. We are actually emitting at all wavelengths. And as I was saying, that this peak of the thermal radiation spectrum is determined by the temperature, because it's determined by the most common collisions in the atoms of this material, right? And if that collision is very intense, if the temperature of the material is very high, it will have very strong collisions so that it will produce photons with short energies. And this kind of things, I mean, if you have something that is perfectly black, or we call that a black body. So this is also called a black body spectrum. So here I have a jargon here that is called a black body. This is what do you call it? Imaginative that is a perfect radiating source that is not doesn't have any features to it. It is able to emit all the energy it absorbs, and it's emitting perfectly at all wavelengths, and then it will make a perfect thermal black body radiation spectrum, which is shown in here. Most material, including the stars, most of solid material we have on Earth and also stars, are not perfect black bodies. Black body is sort of the ideal thing, and we don't. But we don't really. It's not easy to produce a perfect black body. You can do that, but it's not easy to do that. But in sort of theoretically, when we go for the most perfect case, we will get these continuous spectrum that is perfect. So here, I'm just going to use the word thermal radiation, but it's also called black body radiation. So the first phenomena we want to say is that the peak of the thermal radiation is strongly dependent on the temperature of the material, on the temperature of the black body, or the temperature of the star, or the whatever object that you're looking at. As I was saying, that the hotter the temperature, the shorter is the wavelength of the peak of the thermal radiation. So here I'm showing you the spectrum of 3 stars. So you can see a blue star, a yellow star, and a red star. The blue star has the hottest temperature. It's about, the surface temperature is about 11,000 Kelvin. So it's also about 11,000 Celsius. Okay, Kelvin is just a different unit from Celsius in measuring temperature, and I'll tell you how they differ in a minute. But it's about 11,000 Celsius. So this is really, really hot. Stars are really, really hot. This is the temperature like our sun. Our sun have a surface temperature about 5,800 Kelvin. And this is another red star. This is about 2,900 Kelvin. So you can see these 3 stars. They will make spectra that is different from each other. The red star is coolest, and because it's coolest, its peak of the thermal radiation is at the longest wavelengths, because the collisions between the atoms in the star is less energetic than those ones. So those less energetic collisions is going to produce less energetic photons, and less energetic photons meaning longer wavelengths. So that is why its thermal radiation peaks at a longer wavelength than the blue star. Blue star will peak at a blue wavelength. That's also why we call it a blue star, because most of its radiation, most of its light comes from the blue wavelength. And for this star, most of its light comes from the red wavelength, or the longer wavelength, so that it will look red to us, to our eyes. So we call it a red star, and this is a blue star. And our sun is kind of a yellow star. It's sort of in between. Its peak is in the visible spectrum, and it peaks at about 500 nanometer in wavelength, sort of in the middle. And it looks, to our eye, it looks yellow. So that's why we call it a yellow star. So this is called the Weyens law of thermal radiation, that the peak of the thermal radiation depends on temperature and is inversely proportional to temperature. The peak of the wavelength of the thermal radiation gets shorter as the temperature gets hotter. So hotter bodies emit more strongly at shorter wavelengths, and the peak wavelength of the thermal radiation spectrum, or the black body spectrum, is inversely proportional to temperature. And this is the equation that governs that. So the temperature of a black body radiation or a thermal radiation spectrum, like this, a continuous spectrum, times the peak wavelength, the wavelength at which the radiation is strongest, we call that the peak wavelength. And the temperature times that peak wavelength equals to a constant. And this is called the Wien's constant. And so if you want to measure the temperature of a star, you just have to observe its spectrum and then look at where the spectrum peaks. And if it peaks at the blue wavelength, you know it is a hot star. If it peaks at red wavelength, then you know it's a cold star, because the temperature is inversely proportional to the wavelength of the peak of the thermal radiation spectrum. And here there is some unit. The temperature is measured in Kelvin. The wavelength is measured in nanometer. And so this constant have the unit of Kelvin times nanometer. And so that when you put it in the numerator, and when you divide the wavelengths out, you get just a temperature in Kelvin. And so that is the way you can measure temperature of stars. This is one of the many ways of measure temperatures of stars or temperatures of astronomical objects. So we can use that to also try to measure what kind of wavelengths we are emitting at. For example, our human body has an approximate temperature about 37 Celsius. We are not perfect black bodies. We're just approximate black bodies. But anyway, you can get a rough idea of what kind of wavelengths we are emitting at. And first, we need to convert this 37 Celsius into Kelvin. And that is the difference between these two temperature scales. The Kelvin is basically measuring the temperature in an absolute scale, that there is an absolute zero. That is the coldest temperature you can have. It is minus 273 Celsius. So the temperature measured in Kelvin equals to the temperature measured in Celsius plus 273. So our temperature, if measured in the Kelvin scale, is 310 Kelvin. That's 37 plus 273 is 310. And you can put that into the Wien's equation. You can calculate what is the peak wavelength of our human's radiation. And you get a number that is about 9,000 nanometer. That is about 9 micrometers or 9 microns. It's much smaller than a millimeter. And this wavelength is beyond the radiation that our human eye can see. Our human eye can only sense radiation between 390 and 750 nanometer also. So that the radiation that our human body emits is not actually visible to our eyes. So when we see each other, we don't see the thermal radiation that is produced by us. We see the light that is reflected. So that is why we cannot see each other in the dark. But if you can see the infrared radiation, where our radiation peaks, then you would be able to see the person in the dark. So here is a person holding a black plastic bag, a trash bag that is black. You can see this is a picture taken in visible light, that you can see the person, but you cannot see his arm inside the plastic bag. This is taken in visible light, that all the light you can see here are just reflected by the person, that is the reflected ceiling light, right? This is a picture taken using an infrared camera. You don't see these the room walls anymore because they are cooler than the human body, but you can actually see the human body is radiating intensely in infrared. For example, our forehead is hot, and so that you can see this here, the radiation is strongest. And you can also see the plastic bag is transparent in infrared. So this material is like a transparent material when you're looking at it through using infrared light, and so that you can see the person's arm inside the plastic bag. without seeing much of the plastic bag itself. So that we actually glow in the infrared because we have a temperature that is 37 Celsius. There's a question. There was a question earlier. You want to ask again, why for a blue star is peak outside the visible spectrum? Thank you. Okay, for blue star, sorry, we don't see. I mean, we you can say it's a purple star or it's an ultraviolet star. That means its emission is peaked in the ultraviolet, but it doesn't mean. I mean, we usually. I mean, why we call it a blue star, it's just that we call it according to our perspective. We call it according to how it looks to us. I mean, because we can only see this part of the spectrum, we can only see this narrow range. And in this part of the wavelength range, that the star emits more blue light than red light, so it will look blue to us. And for this other star, for this red star, it will emit more energy in the red wavelength than blue, so it looks redder to us. So, I mean, our naming conventions is just depends on how they look to us, what they look like. So it's just our perspective. That's not much. We're not specifically talking about the peak wavelengths. We're just saying that the relative strength between the blue and red. There's another question earlier that is asking about, does electrons at higher energy levels emit light with higher energy? Yes, if they come back to the ground level. So if an electron at higher energy levels go directly to the ground level, they will emit a very high energy level, high energy photons. They can go to violet, they can go to far ultraviolet or even X-ray photons. So that can also happen, yeah. So this next slide actually answers that question of that. Here is a picture of Orion, the Orion constellation. You can see some stars actually have slightly different colors. This picture is actually, this may be a pseudo color, but if you actually go out and look at the Orion constellation at night, you can actually see a tiny, you can notice a difference. The star that is on the right arm of Orion will look redder than the star at the lower right. So that because this star has a much cooler temperature, this is called Betelgeuse. It has a temperature about 3000 K, and this star is called Rigel. It has a temperature about 12,000 K. There's a huge difference between them, and you can see this star looks much bluer than that star. You can actually notice that difference, and if you use color camera to take a picture of this, you can actually notice that slight difference in temperature, in color, and that is why we call these blue stars, and we call those yellow or red stars. Actually, we call it red stars. And so that is the Wien's law, and that is that is talking about the peak radiation of the thermal and peak wavelengths of thermal radiation depends on its temperature. It's inversely proportional to the temperature. Okay, let's end today's lecture here, and we will continue next time. Thank you very much. If you have any questions, you can stay and ask. That's right. The yellow star looks yellow to us, but the peak is at the bluer part of the spectrum. That's right. Yeah. Thank you.